our Ising spins are aligned in two-dimensional square lattice, and if the system temperature is higher than the critical temperature, thermal fluctuation energy dominates over Ising coupling energy. So our spin is completely random. On the other hand, if a temperature is lower than the critical temperature, in this case, all spins are aligned down. So ferromagnetism appeared. And at critical temperature, something very strange sort of pattern emerges. Even such a simple Ising lattice model shows the sort of unique feature of a second-order phase transition. It will allow more efficient communication between distant spins, maximum information storage, the entropy is maximum, and the highest susceptibility for an external input. And all those sort of elements of the criticality suggest that there is something very useful for new type of computing machine. And this was actually the first discovered by the brain scientist, not the physicist. And they sort of claim that the macroscopic order, which eventually leads to cognition and consciousness, is seemingly formed in human brains, which is biased at the critical point due to synaptic plasticity. And our lower panel actually shows the histogram of spatial correlation function for numerical simulation of Ising model. And as you can see that only at the critical point, the correlation length actually scales polynomial, the power law, or scale invariance character. This unique feature was actually reproduced by human brain and the so-called default model. This is our functional MRI data. And those sort of experimental sort of results actually guided them to conclude this sort of bold sort of conclusion. This is the editorial note published in May of this year. Physical Review Letters editorial note actually pointed out this point. I will read this relevant part. Near the critical point, correlations between neurons would occur across all scales, leading to optimized communication. In addition, susceptibility would be greatest there, making the cortex most responsive for physicists and electrical engineers to explore the future computing machine. We are not interested in the wave system or living neurons. We would like to construct such a machine based on optical parametric oscillators. What is this device? This device is very simple, just like a laser. Between two neurons, we put second-order nonlinear crystal, and then second-order nonlinear crystal is pumped by the 2 omega pump field. Then a nonlinear crystal absorbs 1 photon at frequency 2 omega, and simultaneously emit 2 photons at frequency omega. And this degenerate optical parametric oscillator is known to produce squeezed vacuum state below threshold, but at above threshold, the oscillator actually through spontaneous symmetry breaking, take 0-phase oscillation mode or pi-phase oscillation mode. Interestingly enough, at a very critical point of this OPO phase transition, this 0-phase and the pi-phase state coexist as a linear superposition state. This can be easily seen that if we make a projective measurement along p directions by optical combining technique, then our measurement result features a clearly constructive, destructive, constructive, destructive interference between 0 state and pi state. And this sort of superposition of 0 state and the pi state realizes the desired quantum parallel search for combinatorial optimization problems. And moreover, if we mutually couple those OPOs and form the OPO network, then quantum entanglement is formed. And so there is some nice element there for this system. On the other hand, if the system across the critical point and goes to the oscillation at above threshold, then the system becomes digital. Namely, the degenerative function of OPO in a 0 phase or pi phase originate from the interplay between the phase-sensitive amplification and the gain saturation, and allows to stabilize our Ising spin up or down against noise and mechanical fluctuations. The actual idea is shown in this slide. The system consists of one master oscillator and n slave oscillators. And as I said, Ising spin up or down is represented by 0 phase or pi phase oscillation mode in the case of OPO. In the case of laser, it is represented by right and left circular polarizations. In order to implement the Ising Hamiltonian, we can just insert horizontal polarizer or phase shifter, and then that's it. If you further need the DC magnetic field, in other words, the Zeeman term you would like to implement, then you can injection block with a master oscillator with appropriate polarization or phase control. And in this case, the Ising Hamiltonian is mapped onto the overall loss of the laser OPO network, which find the optimum polarization phase configuration with the minimum loss by a Barsag test of photons over 100 to 1,000 generations. The system generates 100 to 1,000 photons and lose them by a loss, and during this process, the system spontaneously finds the lowest loss phase configuration, which is actually corresponding to the ground state of the Ising Hamiltonian. Let me recap the operational principle of coherent Ising machine with this simple picture. Here, the system energy is plotted against all spin configurations. All spins are up to all spins are down. There are 2 to m different spin configurations, and each spin configuration have different eigenenergy. And this energy landscape is plotted here. The task of our computer is to find the ground state with a minimum energy. And the simulated annealing starts from the high temperature and gradually decrease the temperature, and then the residual thermal energy actually help the system to escape from those local minima. And if the cooling velocity is slow enough, eventually system is actually trapped to the ground state. Okay? So in this sort of limiting theorem, the simulated annealing will find the ground state in the extremely long computational time. Quantum annealing is different. In order to use thermal hopping energy, we can apply the transverse magnetic field, and then the spin precess. And this transverse field again gradually decrease, and then the quantum mechanical tunneling is switched off gradually, and then eventually ground state is found. And those 2 approaches, the bottleneck is basically the number of local minima increases exponentially for hard instance in NP programs. So in order to overcome those sort of exponentially increasing number of local minima, the computational time must scale exponentially. We would like to avoid those sort of problem, and for that purpose, we sort of converted the system energy to network loss and put the gain negative temperature from -infinity to -0. Instead of cooling the temperature, but we heat up the system to -0 temperature. And then the system loss and the system gain balance and close to a threshold. Then a linear superposition state between 0 state and pi state is appeared in each OPO. Then 2 to n different spin configurations are prepared in a linear superposition, even in such open dissipating OPOs. And this sort of point only, the gain is equal to loss, so that the instability happens, which eventually leads to single mode oscillation. And after stable single mode oscillation, we can just read out this sort of single mode. And that's basically the idea. When we explained this concept, often people asked the following question: the differential loss or differential energy between ground state and the first excited state also decreases exponentially as a program size. But this is not true. Those sort of energy difference is actually constant if the coupling constant J is actually fixed. This is a case for a relatively small n equal 20 Ising program. There are 1 million spin configurations, and there are numerous local minima, but there are only 2 degenerate ground state. And the energy difference is actually fixed by the Ising coupling constant J. So if we sort of increase the temperature from upward, then we won't miss those 2 degenerate ground states. This is sharp contrast to numerous and dangerous local minima for simulated annealing and quantum annealing, basically. Implementation is a different story. We cannot implement identical OPO optical parametric oscillators of 10,000, 100,000, 1 million, and it is impossible to actually implement connecting optics of 10 to the 12. So here, the idea is basically time division multiplexing and quantum measurement feedback. N optical parametric oscillators are actually formed in common fiber-based ring cavity. Monodrock laser pump pulse sequentially sort of excite the second order nonlinear crystal. Then we have N independent optical parametric oscillator pulses, which is sequentially detected its amplitude and phase by optical homodyne detector. And based on the measurement result, we can compute the coupling term in digital electronic circuit. And based on that information, we can modulate amplitude and phase of the feedback pulse, which is taken from the pump laser and injected back to any sort of a pulse. In this way, we can actually decrease the number of oscillators from N to 1 and the number of connections from N squared to 1. So that's relatively simple to implement this sort. The first implementation of this idea was done at Stanford University, and this is the experimental setup, the first coherent Ising machine. The ring cavity consists of 4 mirrors, free space ring cavity. Round trip time is 16 nanoseconds. The pump modulus laser, fiber modulus laser, has a repetition period of 4 nanoseconds, so we can generate 4 independent OPO pulses. And in this case, we implement 3 optical delay lines. Delay line 1 with 1 bit delay time introduces clockwise nearest neighbor coupling. Delay line 2, 2 bit delay introduces diagonal coupling. And finally, the delay line 3 with 3 bit delay introduces counterclockwise nearest neighbor coupling. In this way, a complete graph can be implemented. Computational result can be detected by the simple differential phase detector, and this is a measurement result. When we implement NP-hard Ising program with n equal 4, success probability to find ground state is larger than 99.9%, which means that we run the system 1,000 times, never fail. So our success probability is 3.9. we recently, the NII people extended this sort of machine to n equals 16 by replacing clock frequency of the pump laser from 250 megahertz to 1 gigahertz. And again, for n equals 16, 1,000 run, no failure. So the success probability is 99.9% or higher. If we use brute force search, the success probability, the worst success probability is 38% and 0.01%. So there is some improvement experimentally confirmed. LTP people actually implemented their large-scale system in their fiber-based ring cavity. Now the cavity is a 1 kilometer optical fiber, and the clock frequency, model frequency of the pump laser is now 2 gigahertz. So that there are approximately 10,000 independent OPO machines are actually running, and those pulses are actually detected by homodyne detector. And this is a homodyne detector output without mutual coupling. At the critical point, the system picks up either 0 phase or pi phase randomly, and the histogram really shows the 50-50% random choice of the oscillation phase. And right panel shows the dynamical behavior. This is a round trip 100. We actually switch on the pump laser. Then our system actually starts from vacuum state and from the squeezed vacuum state or anti-squeezed vacuum state, and then bifurcate into either 0 phase or pi phase. And from here to here, it is about 80 round trips. That is our computational time to get the desired result. Now, how good this machine should be? We actually performed the benchmark study using the numerical simulation. The program is called MaxCut. This is our famous Petersen graph with n equal 10 vertices. Each vertex has 3 edges, so it's a cubic graph. We are asked to cut this sort of graph into 2 subsets in order to maximize the range of the cut. And this program, I will skip the detailed explanation. If we replace the wedge state by the negative Ising coupling constant, the ground state which minimizes the Ising energy, Ising Hamiltonian, is incidentally the solution for maximizing the cut for the given graph. So it is basically a very suitable target for benchmark study. This is our benchmark study result. If we increase the number of vertices from n equal 4 to n equal 20, the number of possible graph increases also 1 to 510,000. We have to solve all of them because we don't know a priori which particular graph is hard. And most of the graph out of 510 graph are easy, and only 5 or 6 graph are really hard. And this table shows the success probability to find the ground state for all those sort of runs. And as you can see that with increasing the graph size, the success probability monotonically decreases, which is a bad sign. But if the network is actually biased at the critical point of OPO phase transition, not at well above threshold, the system enjoys almost constant success probability here, at least up to n equal 20. This number can be compared to the success probability of 10 to the minus 6 for brute force search. So that is the distinct advantage of this approach. If we go to a much larger graph, the ground state we cannot compute because it takes too long. So we can actually use our semi-definite programming, this is actually the popular algorithm, which has 97.8% accuracy guarantee and widely used in modern computer science. And if we solve n equal 800, n equal 4,000 complete graph, and with the same approximation accuracy by simulated annealing coherent Ising machine, the result is shown here. And the computational time as a function of program size is summarized here. SDP actually scales program size n to the power of 3.5, and the simulated annealing scales n squared. And for the program size of n equal 20,000, which is a relatively small problem for computer scientists, it takes 20 days and 100 seconds. If we believe this scaling and scale to 100,000 problem, which is still a small problem for practical application, it takes 5 years and 1 hour. Coherent Ising machine, as I said, it is basically turn-on delay time of OPO network. We switch on the pump and wait for the steady state is reached, and this is approximately 1 millisecond and independent of the program size. Let me switch the gear and talk about our fully homomorphic encryption. This is a very brief summary of cryptography, and it is said in the text. 700 BC, the first crypto system called Scutari appeared in Spartan, introduced by Spartans, and then 50 BC, Caesar ciphers used by Roman Empire, and then a famous Enigma by German military. For the last 2,700 years, the cryptography had been simply a technique for protecting the information in communication channels. And this is because the most of the application area is actually the military, or at most diplomacy. But around 1970, the internet came along, and everyone would like to communicate without sharing the secret key anymore. So 7 years later, the famous RSA was invented, and now everyone can use public key to encode, but only one person can decode with private key.